So good afternoon everyone. So just wait, I am starting. Am I audible, Avinash? Please response, Avinash. Am I audible? Am I audible, Avinash? Avinash, are you hear me?
Yes, sir.
Okay.
Good afternoon, sir.
Yes, good afternoon. Just wait, I am starting.
Okay.
Okay, so good afternoon everyone. So we have discussed in our last classes this our state space analysis, and basically last classes we have to discuss the important topics, that is the rank of a matrix, and also we have to discuss that is the various types of state models in eigenvalue and eigenvectors also. Okay. So today we will discuss also another one. First of all, we have to discuss one problem for the different canonical form. So we have discussed in last classes the different canonical form. Okay. So this different canonical form, you have to know there are the 4 canonical forms are available. So I'm just written here. Canonical forms for a discrete time state space equations. Okay, so these topics we have to discuss in our last week also. So you know that here are 4 types of canonical forms we have to discuss. First one is controllable canonical form. Number 2, that is observable canonical form. Number 3, that is diagonal canonical form. And number 4, Jordan canonical form. So these 4 types of canonical form we have discussed in our last week also. So using this canonical form, for you have to solve any discrete time state space equations. Okay. So we have discussed in last classes is broadly one by one. Now we have to take one example using this canonical form. So Question is given here. Consider the following system. Consider the following system. You have to given this question, that is y of j by uj, that is output y, input equations, that is transfer functions. You know that here we have to express as Gauss transfer functions, that is z plus 1 by z square 1.3z plus 0.4. So question is given the state space representation in the controllable canonical form. Observable, observable canonical form. And diagonal canonical form. Okay. So आपको ऐसे क्वेश्चन दिया जाएगा, that is the false transfer functions yz by uz. This is the required equations. So you have to find using the different canonical form. So the state space representation for the first one we have to calculate for controllable canonical form, number 2 observable canonical form, and number 3 is the diagonal canonical. Okay. So what have to do? So this is very easy question. So first we have to express the controllable canonical form. Okay, so you know we have to express these canonical equations in the matrix form. So first we have to express these equations for the matrix form. So first one is x1 k plus 1. Another one you know, that is x2 k plus 1 within matrix symbols. Then we have to calculate from these equations the value of this, that is, you know that first is 0 and 1, another one is minus 0.4, another one is minus 1.3. This one and also this one also. So matrix signs. So this is for the first x1k and this is x2k. And another one you have to show, that is 0 and 1. It is for the u. So this is the input functions of the given functions we have to given in the questions for the controllable canonical. Okay. Next, what is the output of this controllable canonical form? That is yk. You know, this is the 1 1. This is not point. This 1 and 1, and you know this is first one x1k, second one is x2. So this is the basically matrix representations of given equations for the controllable canonical form. Okay, so first we have to calculate the controllable canonical form. Okay. Next, number B, you have to find observable canonical form. Okay, so now we have to make the matrix in the observable canonical form. So we know same two variables, that is first one is x1 and another one is the x2, that is x1 a plus 1, x2 a plus 1. The value, you know that this is interchange for the previous one, that is 0 and 1. Then also here minus 0.4 and minus 1.3. It is interchange the previous one. Previous we have to written here, you can see this is 0 1 minus 0.4 minus 1.3, and here also the row it is considered here column. Okay, so this is the basically interchange for the observable canonical form, and previous one is controllable canonical form. Okay, so this is for the x1k and x2k. This is same 1 and 1 for the UK. This is the input functions of the input matrix of the observable canonical form. And what is the output of the equations? That is yk, you know that this is 0 and 1. Okay, and it is for x1k and x2. So this is the matrix form of the observable canonical form of the given equations. Okay, is it clear? Now the third one is diagonal. Third one is diagonal canonical form. Okay, so the given pulse transfer function which one? The given questions, that is z plus 1 by z square plus 1.3 z plus 0.4. Okay, so functions, that is we have to express here yz by uz can be expanded as follows. Okay, so we have to written this equation just like you can see, that is yz by uz. This is 5 by 3 that by z plus 0.5 plus minus 2 by 3, that is z plus 0.8. You have to calculate these two equations. You have to find the questions. The question is given here, this one. Okay, so you simplified the these equations. You have to expression is received from the expression from this one. So we have to express this equation, these pulse transfer functions as per our diagonal format. This now you have to make the matrix form of the given equations. So you know that is first one a variable is x1, second variable is x2, that is a plus 1. Sorry. This is minus 0.50, then 0, another 0, this is minus 0.3. So this is the basically first one, z is equal to minus 0.5, another one z is equal to minus 0.3. Okay, and this is a diagonal canonical form, so diagonally it is also same to same, that is 0 and 0. Okay, so that's why it is called the diagonal canonical form. So this is for the first one x1k, another one is x2k. Okay, and this is 111. uk. This is the input functions of the diagonal canonical form, and output is yk. This is the 5/3. This one, another one is the minus 2/3. This one. So this is for x1k and x2. Okay, so this is the answer. So I am repeats once again. Those who have late coming to the class. So you have to given we previously discussed the canonical form in our discrete time state space equation in previous week. So this fourth type of canonical form we have to express different fast transfer functions, that is controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical. So now we take we given a one example. So ऐसे आपको question दिया जाएगा. Consider the following state space equations or fast transfer functions. The state space representation in the first you have to convert controllable canonical form. Number two observable. Number third is diagonal. So first we have to consider for the controllable canonical form. You know that format. This is the two variable format, that is x1 and x2. First one 0 and 1, and this is the minus 0.4 and minus 1.3 from coming. Another one is the 0 and 1 or 2. This is the input functions. Then we have to express the output of the equation, that is yk, that is 1 and 1, x1 and x2 variable. Number two, method of observable canonical form. This is same to same, but the previous row is changes here column. Okay, so that's why 0 and 1, minus 0.4, minus 1.3. This is 1 and 1. Okay, so this is the basic changes of the two methods. And this one is the diagonal canonical form. So, is it clear, all of you? That type of questions are coming in your semester. So this is very easy. Please practice in your rooms, in your books. Okay. तो ये किताब में बहुत सारे एग्जाम्पल है. So please everyone practice one by one. Then the concept is totally clear. Now we have to go the another topics in this module. So there are different solution of discrete state equations. That means we have to express here different types of state space equations. Okay. So now we have to solve non-uniqueness of state space representation. Okay, so you have to given a pulse transfer functions, okay, of the any system. The state space representation is not unique. Okay, so we have demonstrated that different state space representation for a given pulse transfer functions system is possible. Okay, so first of all, we have to define the pulse transfer functions. So for a given pulse transfer function system, the state space representation is not unique. Okay. We have demonstrated that different types of state space equation for a given transfer function, given pulse transfer function. So consider the system defined by first is input functions, that is x of k plus 1. This is equal to coefficient of g, that is xk plus h u. This is equation number 1. And output equations, that is yk, this is the c of xk plus d of u. Okay, so you know that here g, h, c, d, these are the basically coefficient. Okay, coefficient of the basically input and output functions. So this is a equation number 2. Now let 1 minute. 1 minute. Just wait. Let us define a new state vector You know that we have to express the vector symbol, this one, that is the x vector. Okay, that is new state variable state vector, that is x vector k by, that is the equations we have to express, that is x of k, this is p into x vector k. This is equation number 3. Now here p is a non-singular matrix. Is a non-singular matrix. Okay. Now what have to do? We have to substitute the equation, that is 3, to the equation 1. So now by substituting equation 3 into equation 1, we obtain. So now you have to consider here, that is equation 3 to equation 1. So now you have to see here. So the equation is coming p x vector k plus 1. This is equal to g p x vector k plus h of u k. This is the another number, equation number. So this is very easy. So you have to express here xk is equal to p x vector k. So we have to express this x of k into this equation. So equation is coming here, p x vector k plus 1 is equal to g p x vector of k plus, that is h of u. Okay. Now next, pre-multiplying both sides of equation, that is last equation, that is equation 4, by p inverse. Okay, so in get, so we have to multiply, that is p inverse in the equation number 4. So equation 4 is coming, that is x vector of k plus 1 this is equal to P inverse G P x, this is P x vector of K plus P inverse H U. This is another number 4. So you can see these equations. So this is the basically required equations. Now we have to take the both sides for the P multiplying the P inverse. So P inverse when is coming, that is P and P is cutting down. Another this is P. So this is the basically equations is coming. X vector 50 plus 1 this one. Now, so from this equation, let us define. So P inverse GP is equal to G vector. This one here you can see everyone P inverse GP. This is basically we have space here G vector, and another one P inverse H. This is equal to we have to take here H vector. So this is a H vector and this is a basically G vector. So now the equation 5, this one, this is 5 equation can be written as follows. This is X vector A plus 1, this one, then is equal to, you know that here P inverse GP, this is the G vector. So G vector, then X vector K, then this one P inverse H, this is the H vector. So H vector of K. Okay, is it clear all of you? Please response me, is it clear up to this part? No one is response. Anima Kumari, is it clear? Anima, Ankita, Anshu, are you here being?
Yes, sir.
So please respond everyone. Okay, so this is the basically equation is coming from, apply this to, so this is the equation 6. Now, so up to this part, this is the input functions. Okay, this x you know that x of K plus 1 or x of K, this is the input function. Now we have to consider for the output equation. So similarly, by substituting equation, that is equation 3 into equation 2. I am show the equations, just wait. We obtain, because you know equation 3, this one, and equation 2, this is the output equation, that is y2. Now we have to consider for these two equations, equation 2 and equation 3. So we have to written the equation, that is yk, this is equal to cp x vector of A plus d of U. Okay, this is another number. So equation number 6, that is 7. Okay, so we have to substitute in the equation 2 and equation 3. We have obtained the output equation, that is y of k cp x vector plus x vector k plus d. Okay, so now by defining this equation, that is cp, this is the c vector and d is equal to, we have to express here d vector. So we can write equation 7, this equation as, that is yk is equal to c vector x vector of k, this one, and d vector uk plus d vector uk. This is another number 8. Okay, up to this part it is clear, all of you. So now here you can see, so first previous equations we have to express input and output, this one and this one. Now this input and output equation, you can see here changes. One is this one, the vector notation, using the vector notation. Another one is the this one. Okay, so now we have to written the equations, then you have to clear idea. So we have has shown the state space representation given by equation, that is equation 1 and equation 2. क्या था उसमें, ये था that is x of k plus 1, this is equal to, you know, g of xk plus h of uk, and output equation क्या था, that is yk, this is equal to c of xk plus g of uk. Now we have to apply the vector analysis, test space representation. The equation is coming. So this is equivalent to the state space representation given by equation that is our final equation. We have to see. I am just going the before page. That is equation 6 and equation 8. 6 and equation 8. So क्या आया था, that is x vector a plus 1, this is equal to, I think, g vector x vector k plus h vector u of k. This is input function, and output is, that is y of k c vector x vector c vector x vector of k plus t vector u of. Okay, so this is the basically similar equations. First we have to express for the past transfer functions, then we have to apply the state space representation of the vector method. So now we have to express this equation, this part. Okay, is it clear? So this question is very important. Question ऐसे आप लोगों को आएगा. So what is the state space equations for non-uniqueness pulse transfer functions? तभी आपको ये वाला solve करके आपको दिखाना पड़ेगा. This is very much easy. So practice once again. So I think it is also clear. Okay. Is it okay, all of you?
Yes, sir.
Yes, sir.
Okay. Next. Equation for the discrete time states equation. So this is another topic. A discrete. So everyone write your own name and roll number in the chat box. And Pranab is present.
Yes, sir.
You take a screenshot, okay? So discrete time state space equations. ऐसे क्वेश्चन दिया जाएगा, what is discrete time state space equations? So you know that we have to express the linear time invariant discrete equations. So the linear time invariant discrete time state equation is, that is x of k plus 1, this is equal to g of xk plus hk. Okay, so now we know that we have to express the formula, that is diagonal matrix, that is zi minus g inverse. So by a recursion procedure and then the Z transform method is computing, that is zi minus g inverse. So finally we treat the solution of the linear time varying discrete time state equation is x of k plus 1. This is also gk xk plus hk and u. So this is the basically one discrete time state equations. Okay, so here you know that this k is also changes the different ranges, that is 0, 1, 2, dot positive infinite range, that is number of n terms. Okay, so this is the basically discrete time state equations. Okay, so next class we have to solve the another discrete time state equations, that is linear time, how to solve the linear time invariant discrete time state equations. Okay, then another topics is available, state transition matrix. So these two topics are remaining for the last in this module. Okay, so next classes, that is Friday, we have to discuss these two topics. Okay, so I am upload the class notes in the Google Classroom portal, so everyone see this class note and also practice more and more problem. Is it available in your books? Okay, so I am uploaded also this books scan copy in your Google Classroom portal. Okay, so Anyone, any doubt or any questions, so please ask me. No questions, anyone? Okay, so I conclude the session. Okay, thank you everyone.
Thank you, sir.
Thank you, sir. Thank you, sir.